So these are the topics that we shall be, these are the general topics that we shall be covering today. I'll spend a very small amount of time talking about what MIDAS IT is and what our software is. Most of the time I will be spent discussing about the modeling philosophy, the design philosophy of the Eurocode and the specifications that the Eurocode prescribes. And finally, I shall discuss a little bit about the differences between the BS code and the Eurocode for composite structure design. So about MIDAS IT, we have been developing programs since 1989, and the programs became commercially available starting 1996. We are headquartered currently in South Korea at Seoul, and we also have corporate offices in Beijing, Shanghai, Detroit, Dallas, Europe, India, and Japan. So we are one of the largest civil analysis software developers with a proven reliability of over 5,000 project applications. We have intensive quality control systems, analyses, and design specifications have been verified by various institutions. And also, we shall be soon opening a branch office in Singapore, starting early next month. So what is MIDAS Civil? Now, most softwares that are available out there, most finite element softwares are very, very specific. They are quite limited in their application range. MIDAS Civil is a complete solution, but not only for bridge engineers. It is a finite element solution which you can use for making general purpose structures like silos, tanks. You can make 3D models. You can do underground tunnel analysis. And of course, it is catered to the bridge engineer. So you have specialized tools available for you, which you can use to very quickly create your model, analyze and design if your model is a bridge. So coming on to what types of bridges that MIDAS Civil can handle. These include from the conventional bridges like culverts, frames, slab, girder bridges, to the more complex bridges like the balanced cantilever bridge, the incremental launching method, movable scaffolding, and so on, and to some of the most complex bridges like cable-stayed, extradosed, and suspension bridges. So although it is not, I have not shown it in the slide, a few worthy project applications include the Sutong cable-stayed bridge, which is one of the longest cable-stayed bridges currently in existence today in China, the Ruski Island Bridge, which is the longest cable-stayed bridge currently in existence, and so these are some of the top bridges that have been built with the aid of MIDAS Civil. So that's pretty much it about about our company and about our software. I'll jump right in to the crux of our discussion topic today, starting with the modeling philosophy behind steel girder bridges. So it's pretty obvious to anyone who's been in this industry for a while that there are three main modeling methods available when you use a software: 2D grillage models, 3D grillage models, or a meshed finite element model. So each of them have their advantages and disadvantages. I'll discuss them briefly over here. So 2D grillage is the most common modeling method and one of the most preferred as well. So this grillage is either modeled as an orthogonal or as a skewed grillage depending on the site requirements, and from your slides you can very easily see what the prescribed recommendations usually are. Now in grillages with skew angles exceeding 20 degrees, it is often said that local analysis should be catered to and should be done, especially at the obtuse angled corners, since the grillage cannot separate torsional effects carried by the slab from those carried by the beam in warping, which is a very major concern in these regions. And some of the additional points are the usual grillage modeling principles are applicable. For multi-girder bridges, shear lag is unlikely to reduce the effective slab width below the actual width, However, for models with bare steel condition, it is advisable to have short-term composite condition and long-term composite condition separately. Section properties for the composite beams should use the full composite second moment of inertia, and intermediate longitudinal elements should only be given the properties of the slab. And this one point is directly out from the book of E.C. Hambley. Torsional stiffness of the slab should be equally divided between transverse and longitudinal beams. And intermediate bracings should be modeled because they affect the local transverse bending stiffness. Coming on to 3D grillages. Now, why do we require 3D grillage? Since, as you know, I've already mentioned that a 2D grillage is not really able to capture the local effects of deflections of cross girders and their interaction with the lateral bending of the flange of the bottom flange of the main girders. So in this respect, 3D grillages are quite useful, especially when you deal with ladder deck bridges. So the basic modeling procedure is outlined in this slide. That vertical bending is assigned wholly to the upper members, while bottom flange elements represent only the plan bending of these flanges. And although this model captures the local effects in a better fashion, it is still not able to separate the global and local effects. You cannot separate them from one another. They appear to you as a combined effect. So the last is the finite element modeling, arguably the most accurate and conversely the most complex of the three modeling procedures. So needless to say, it is much more realistic with respect to the results that it provides. A very accurate representation of local and global responses can be made if the mesh is of good enough quality. Models can be built using a combination of beam and plate elements. So one possible combination, for example, plate elements being used in the slab and the web, while beam elements are used in the top and bottom flanges. So a few points about construction stage analysis. Now, there are several actions on any structure that are not normally accounted for without construction stage analysis, such as creep shrinkage, locked-in stresses, pre-stress losses, accounting for the pouring sequence of the deck slab, and accurate deflections, particularly those affecting cable. Of course, in elaborating these points, I am assuming that time is not considered without construction stage analysis. Of course, in manual modeling, in manual considerations, we do consider time without actually considering the construction stage analysis, but most finite element softwares today do not separate the two. So for composite structures, particularly for our topic of discussion, steel I-girder composite bridges in particular are extremely sensitive to the pouring sequence, creep, shrinkage, strength variation, and locked-in stresses. Now, the pouring sequence of the deck is usually quite straightforward for a straight composite bridge, but for curved multi-span bridges, the deck is poured in different stages at different locations, and this needs to be planned very, very properly and very carefully, because this can significantly affect the design forces, the overall design of the bridge that you are modeling. Okay, so before going on to the actual design philosophy, let me show you our product, that's MIDAS Civil. In fact, let me show you this particular model. So this model here is actually a model for a simple two-span straight bridge, which has been modeled with abutment and pile foundations. For those of you who have used MIDAS softwares previously, you will be aware of how intuitive and how easy the interface is. For those of you who are new to the software, who are seeing it for the first time today, we hope you will appreciate the useful features and the general ease with which the software allows you to work. So The main purpose of my showing you this model was just to outline the basic capabilities of MIDAS, and that this is definitely not the only, this is definitely not the best that the software can do. The software is capable of infinitely more than what is being shown here. In this particular model itself, we have we have assigned it time-dependent properties, we have assigned it a reinforcement, tapered sections, we have assigned it construction stages, and we have also done preliminary soil structure interaction using multilinear links, like so. I'll show you how these stages are varying now, how MIDAS shows this. For example, the first stage, this is the steel only stage, where if I zoom in now, you'll notice that only the steel girders are present. In the second stage, when the second stage, the concrete is poured, and at the end of the second stage, when the formwork is removed, you can very clearly see that the deck is indeed cast over the girders, and the composite action has now been initiated. So I will start showing you. Let me go ahead and open up a new model, and I will show you a very simplistic model that I will create on the fly, which will hopefully demonstrate to you the effectiveness of MIDAS Civil. Okay, so first off, I'll define a point grid for myself. Now, I will not be going into too much detail about what is the procedure that I am using and what exactly I am doing. So if at any point you have any questions or queries, you can just go ahead and type it out into questions box. So right now I'm just defining a simple point grid. That is a 1 meter by 1 meter grid. What I'll do is I'll make a 2-span 30-meter long bridge with 3 composite girders side by side with a center to center spacing of 3 meters. So I've created one longitudinal girder. Let me turn off the point grid. And I will copy it twice in the lateral direction. So I've got three girders like so. Now the material and section properties I am going to import from a previously created model file. So I'm not going to bother with creating the material from scratch. I can do that if I want, but it is much more easier for me to just import the materials and the section properties from a file that I have created previously. So as you can see, as soon as I imported it, MIDAS automatically assigned it as well. So here I have assigned 3 different kinds of materials. One is the SRC, the steel reinforced concrete material, which I need for composite section design. As you can see, the standards are Eurocode for both of them. I've created a material for my steel bracings that I shall be giving at the abutment ends. I've created a crossbeam deck property, which I will be using for modeling my cross girders. And I've created certain section properties as well. So this is the composite steel. This is how the composite section property is defined. So you just define the normal steel eye girder property and just define the slab parameters above it. Okay. So now what I'm going to do is I'm just going to divide my section, let's say into 10 parts. And simultaneously, let's say just over here, simultaneously, I'm going to drop some nodes at an unequal distance in z direction. I'll shortly explain why I'm doing this and exactly what I am doing. So I've entered the distances like so. And when I click apply, 2 additional nodes are created. Now what I've done is my section offset is at the top of the section, but my support will definitely exist at the bottom of the section. So I've created an additional node at the bottom of the section for referencing it so that I can create the support condition below that node. I'm assuming that my bearing height, the total bearing height will be 0.2 meters, including the bearing and the basic support. Right. Now, let me go ahead and create my crossbeam properties. So I'm just going to choose crossbeam deck and the crossbeam property. Let me just create one element and translate this 8 times ahead. And I don't even need to measure out how much the distance has to be. I know it's 3 meters, but I can just click it once and then just click on the 2 nodes so that MIDAS automatically takes the distance, intersecting all nodes and elements. Sorry. And copy it 8 times. Okay. So you can also check it from the slab, slab view. You can see how it has been modeled now. Finally, going into the left view, I'm going to translate this node in the y direction unequal times again. So 1.5, 3. So first it will in the y direction 1.5, 3. So first it translates it at 1.5 meter, and then at the newly created node that is 1.5 meter from the initial distance, it takes 3 meters ahead of that. So 1.5 and then 3 meters ahead. So now we are free to create the bracings. So I'm going to create the brace. I've chosen a British section, a British code UB section. And I'm going to create my bracings in this fashion. Like so. Now I'm going to copy these bracings, translate the elements over to the middle and to the end. Okay, so before I do that, let me just go ahead and delete these 2 elements because I do not need them over here. So the brace, copy it 15 and just 2 times. So it will first copy it at 15 and then at 30. Intersect any node or element that it encounters. So you can see we have our basic model ready for us. And finally, I'll just translate these nodes as well. Twice, right? So you can check it in the 3D view, how it is basically looking. Okay, so now we'll need to create some boundary conditions, some support conditions. So first off, let's create some rigid link properties. We need to rigidly connect the top of our I section to the bottom of our I section. Not only because it's part of the same section, but also because this it is the only way. If the bottom of the section is not it's not connected to the top of it, the diaphragm portion, the U-beams, the bracings, they will not be as effective when you conduct the analysis. So let's connect it, and I'm going to copy this rigid link minus 3, minus 3. So again, the same thing. I'm creating the link over here where my mouse is right now, and I've entered minus 3, minus 3, which means on the other two girders as well, this link that I create over here will be copied. Let me select this. So that's 1. That's 2. Let me save this. And that's 3. Now finally, I'll create my bearing property. So I'm using the elastic link condition, which is basically a spring in 6 degrees of freedom. So I'm going to define one of the supports as a pin support, one of the support points as a support regions as a pin support, and the rest will be roller support. So I'm taking the mid region as the pin support. Sorry. Okay. And the rest I'll be taking as roller support. So from here I can see the lateral direction, or rather the longitudinal direction, is the local z-axis. So I put it as 0. Now I want it to be laterally free in the y direction. And for the rest, it will only be 0. So why have I assigned it lateral, no lateral restraint in the y direction for these two regions is because I want to account for temperature actions as well. So the temperature actions will cause longitudinal as well as lateral flexure. So it should be free to expand in the lateral as well as in the longitudinal directions. Finally, we go ahead and we assign the boundary conditions, the final support conditions. So I'm going to create it as a fixed support. Okay, so this was so the support is now pretty much fixed, and we have just completed the modeling aspects. I'm going to create a few structure groups because now I'm going to start with the construction stage modeling. So I'm going to create a few structure groups. Let me say all, cross beams only, and all cross beams. So in this model, I'm going to show some very basic load cases like self-weight, parapet loadings, additional structural loadings, temperature loadings, construction stage loads, and I'm also going to talk about moving loads. Of course, the moving loads will be as per the Eurocode. Right. So all naturally means everything. From this all, I'm actually just going to unselect the cross beam. So why I did the unselect the cross beams, it will become apparent when I do construction stages. Cross beams only, just the cross beams, and cross beams and the brace. From the brace, I will remove any links that are below the XY plane. So basically these are the all the cross members. Similarly, boundary group, just put in everything. Now for loadings, I will create a few groups like self-weight, parapet loading, temperature loads, or any other loads that might come in. The moving load I will not need to create because it is created automatically when I assign moving load data. Okay, so static load cases. I'm going to create load cases. So I'm going to create a self-weight load case, a load case for the parapet, which will be of dead load component and attachments, temperature load case. So I'm going to put it as temperature. So for demonstration purposes, I'm not considering very many cases, but for any kind of model, for any complexity, regardless of what it is, MIDAS Civil can handle near about everything. All right, so let's go on to assigning the weights, assigning the cases now. So this is in the load group self-weight. And I'm just putting it as -1. I'm only assigning it a direction because MIDAS already knows the value of the self-weight, because in the material definitions, the unit weight of the material is also defined. So MIDAS automatically calculates the value of the self-weight. All it needs is a direction to put it in. So now that that's done, let's go for the element loads. So although I've named it as parapet, I'm assuming that this load will include just about, I'm going to add the other loadings under the parapet load case as well. So let's say -5. Now I've used a function that is active deactive. I've only activated the main girders. Active deactive, you can think of activation as going through the layers in AutoCAD. Like if you want to work only in a particular layer, you just hide away all the other layers. Activation is basically the same thing. I'm only working with a particular part of the model. The rest is unaffected. So I select the end beams and apply a unit load on it. Similarly, if let's say my carriageway loading is -1.2 or something, so I've added that as well. So this is my parapet loading now. I've reactivated everything in my model, and the final load will be the temperature loading. So I'm just going to assign it a system temperature, and I want it to vary between, first let me change the units from Fahrenheit to Celsius. So I want it to have, let's say, a 30-degree variation. So let me change load case to temperature and this to temperature as well. So globally, the entire model will have a 30-degree temperature variation, and it will expand or contract depending upon the boundary conditions. Okay, so these 3 load cases have been defined for us. For any load case or for anything, you can always have element tables. So you can just right click, go to tables and get into the element tables as well. You also have tables for nodes and elements. So if you have like in any model, if you have AutoCAD model or something, or if you have the coordinates of your model, you can just copy paste it directly. The element table, or basically any table in MIDAS Civil, works exactly the same way as it would in Excel. Control C in Excel, Control V in MIDAS, or Control C in MIDAS, Control V in Excel. They both work interchangeably. The last thing before dealing with construction stage analysis is assigning creep shrinkage and time-dependent material effects. So creep shrinkage. Now I'm going to use the CB-FIP code. However, the European code is also available. Just for simplicity purposes, I'm going to go with the CB-FIP code, which incidentally even the British code recommends, simply because the European code is, let's say, it is quite complex, and it requires a lot more data entry. Incidentally, the CB-FIP code is slightly less conservative than the Euro code for material grades lower than C25, but beyond that, the CB-FIP code becomes more conservative, and the European code becomes less. So 25,000. I'm not going to bother with the notational size right now. Also, another point of interest is that the CB-FIP code and the Euro code are pretty much the same, almost entirely the same for the building generation particularly. The only point of difference, as I had mentioned, is that that beyond a certain grade of concrete, beyond C2530, the European code adds alpha and beta factors to the creep coefficients. Okay, so although my material grade is C25, so by rights it should be 25,000 should be its compressive strength. But when entering compressive strength under CB-FIP, we have to take care that it's mean compressive and not the characteristic compressive. So the additional mean compressive always adds an extra 8 MPa to the characteristic strength. So creep strength, and I'm going to assign it to the beam concrete material. Now, a few points I should mention here. I've created creep properties. I've assigned the creep property as well. I've created compressive strength properties, time varying compressive strength properties. I've assigned those as well. But in the works tree, you may notice that some entries are being highlighted in blue. This is one of the user-friendly features of MIDAS, that when an element or when an entry is not assigned to your model, it is highlighted in blue color. So that means the two materials that we see here, beam concrete and beam steel, have not yet been assigned to the model. So the question arises, I have assigned the creep and shrinkage and the time-dependent properties to the beam concrete material, and yet the beam concrete material is not yet assigned to my model. So what's going on? This will become apparent to you when I create the composite section for construction stage properties. So right now, before that, I'm going to create first the construction stage property, construction stage itself. So stage 1, let's say with a duration of 0 days. It does not matter because I'm only adding the steel section property, right? So I'm activating the group that is only steel, boundary group, all my boundary, and just the self weight on the first day. So this is stage 1. Stage 2, I'm considering is the stage when my deck is poured and the concrete is cast and the formwork is removed. So 30 days in, I'm assuming that the cross beams only they will have, let's say, an age of 10 days. So the cross beams only have now been activated, and the cross beams represent the stiffness of the deck in the transverse direction. Boundaries and etc. are as they were. Parapet I'll start to add at the last day. Apply. Finally, in stage 3, let's say give it a duration of 10,000 days. Okay, I can add the temperature loading in the first day. It does not matter. Now here, the construction stage goes something like this. So stage 1, this is stage 2, and this is stage 3. Now something is off here. You see, in stage 1, we should expect that there is no deck, and yet the software is displaying for us the composite deck. So the transparent lines, the transparent white lines in the model, they represent the deck section. So why is the deck still active here? So the reason is we have to do one additional step in order to separate the deck in the construction sequence. That is, we have to define the composite sections in the construction stage. So I click on add. Since here I have only one construction stage, I will once a composite section. MIDAS can automatically differentiate between the different parts that have to be activated at different intervals. So part 1 is the steel part, part 2 is the concrete part. I'm going to define them both on a material basis, and part 1, that is the steel part, will have the property of beam steel. Part 2, that is the concrete part, will have a property of beam concrete, and it will have an age of 10 days. So this is where the creep being assigned to an unassigned material is resolved. Although the material is still not directly assigned, it will be used, and its creep parameters will also be taken into account when construction stage analysis is performed. And active stage will be stage 2. So active stage, what does it mean? In stage 1, I must have only and only my steel section. My concrete section, my concrete part should not exist in my composite structure. In stage 2, the deck is cast, the formwork is removed, so my composite action starts to happen from the start of stage 2. So I put the composite stage as stage 2. Let me update all H. So the notational sizes are automatically updated when I click on that function. So here you can see the notational size H is automatically updated. And the notational size is used for creep calculations by both the European creep codes as well as the CBFIP code. So once again, if we go ahead and if we check, now you can see in stage 1, the difference is very, very palpable. You can see that there is no deck section now. In stage 2, there is indeed a deck section. In stage 3, that is just a very long stage for consideration of the time-dependent effects. The final parameter the final loading that I will show you in this model is moving loads. So coming over to the moving load part. So MIDAS Civil supports a very, very large variety of codes, right from the Ashtal RFD to the Canadian code, to the Russian code, the Indian code, the British as well as the European code moving loads are supported. So for those of you who are using the British code, you can use the BS moving loads. For those of you who are switching over to the Euro codes, for example, like our Singaporean viewers, you may want to use the Eurocode load application feature. So define traffic lanes. So Again, moving load analysis in MIDAS is a three-step process. You define a traffic lane, you define a vehicle, and you define a moving load case. So I'm going to define two traffic lanes. Let's say with an eccentricity of minus 1.5 meters. And here I'm going to choose vehicle load distribution as all cross beams. Now, what is the difference between these two, lane element and cross beam? So the lane element vehicle distribution means that the vehicle loads will only and only be applied to the assigned elements. They will not be redistributed if it is a grillage model. If you want to redistribute the vehicle loadings, if you want the load path to be like first from the cross beams and then to the longitudinal beams and then to the supports, as it normally is in a grillage model, you would need to define a structure group for cross beams or for the cross members and then select that structure group from all cross beams. Furthermore, the lanes can also account for skew. You can have either simply a forward or a backward moving direction or take both into account. So right now I'm just going to select it like so and give it a lane name, let's say lane 1. So that's lane 1. Similarly, I'm going to create a second lane on the other side. That will be lane 2. Name it as lane 2. So I've got 2 lanes now. Coming on over to the vehicles. So MIDAS Civil completely supports all the Eurocode load models. We have paid particular attention to the UK model currently, and we are working towards implementation of other annexes as well. Currently, MIDAS supports the recommended annex, the UK national annex. We have limited support for the Italian annex as well, and we are currently developing in the process of development for the Singapore annex. So I'll create two load model types, LM1 and LM3. So LM1 is basically, you can think of it as the rough equivalent of the British KEL loading, the KEL plus the lane load, whereas LM3 is a specific load model defined only for fatigue analysis as per the Eurocodes. Finally, we define the moving load cases. So case 1, just the load model 1, and case 2 will be LM1 plus LM3. So load model 1 and load model 3 moving in tandem. Okay, so in this way, we have basically defined all of our complete model has been defined, and we are now ready to conduct the analysis. Beg my pardon. So we will conduct the analysis now. Now, MIDAS softwares also now support 64-bit operating systems and multiprocessor systems, which are pretty much the norm today. So by default, MIDAS has been optimized for dual-core processors, but if you have a quad-core configuration, you can manually specify the quad-core configuration from the analysis options. So you can have it like a multiprocessor, and you can choose the number of processors as 4, and you can also specify the amount of RAM that the program would require. All right then, so we've just conducted the analysis, and finally we can see our results. So the normal results are pretty much obvious: the bending moment diagrams, the shear force diagrams, My, Fy, and Fx, so on, and Fz. So all of these diagrams are pretty much the norm. You can also check for reactions. Now, what we would be interested in seeing are the construction stage results. So at construction stage, MIDAS offers you construction stage results of these kinds. So you can separately see the dead load, the erection load, creep secondary, shrinkage secondary, and so on. So for example, creep secondary loadings. So the reactions due to creep, the secondary effects of creep can be seen. You can see the secondary effects of creep forces. Similarly for shrinkage as well. And you can separately see these effects for parts 1 and 2. Part 1 being your steel member and part 2 being your concrete slab. So you can separately get the design forces for the concrete and for the steel, which is very useful when you go for the actual design of a composite member. Okay. So from the analysis option, of course, you can glance over at some of the other capabilities that MIDAS Civil has to offer. So you can see P delta analysis, buckling, full eigenvalue buckling analysis is possible. Heat of hydration is also possible with MIDAS Civil. You can do advanced heat of hydration analysis for very high grades of concrete. Nonlinear analysis catering to both geometric as well as material nonlinear analysis is possible. And approximate tendon loss, this is just one of the provisions prescribed by the American PCI code, which is also supported. Right. Now, let's go over and let's try to see the moving load results. So by default, MIDAS will show you only in the post-CS stage the moving load result cases, the absolute maximum results. Now, normally people are also interested not just in the absolute maximum, but in the concurrent reactions. So in order to save time, MIDAS does not directly give you the concurrent reactions, but if you want it from the analysis control, you can choose this option, normal plus concurrent forces, reanalyze, and you can get the concurrent reactions for concurrent forces and stresses as well. And you can also apply calculation filters. For example, people are not normally interested in the displacements caused due to the moving load. So you can check it off and the analysis will just become a bit faster. Finally, we have what is called the moving load tracer. So if you are interested in the vehicle position that is causing a particular moment value in an element, let's say here I'm getting the maximum moment value. So what is the vehicle position that is causing this maximum moment value? So I just click that element and I click apply. And here it shows me the vehicle position along with the influence line that is causing that maximum value at that particular element. Finally, you also have, I can show you, is the bridge girder diagram. So the bridge girder diagram is pretty much basically a variation of stresses. But what this also allows is you have the option of drawing the allowable stress line. So when you click on like apply, I will have to assign a small structure group to show you this. So let me just reassign a structure group. For example, this particular group. going back to the bridge girder diagram, any particular stage. So the last step in that stage, structure group 4. So for a particular load case, it gives you the stress variation. For example, I'm just checking the actual stress right now, and it gives you the permissible stress limits as well. So if I want to check the combined stresses, so it will give you the combined maximum value, and it will tell you whether it is exceeding the stresses or not. So this is also a very useful feature. And aside from this, you can, of course, you can get the result tables for each and every variable that you might have. So for example, forces and stresses, you can get the bearing reaction. So from elastic link, you can get the reactions in the bearings. So what is the actual force in the bearing, the shear force, the moments, the torsion, etc. And each of these tables is Excel compatible. For example, you have the option of exporting to Excel, or what you would probably prefer is simply copy it over here. Just right click and copy, and go to any Excel sheet and just paste it. Control V. That's all you would need to do. Okay, now we can shift over to the design philosophy, the particular codes in the Eurocode that are of interest to our current model. So first off, let me start with the required design codes. So in general, just a brief overview of the major codes that are required. So these include, I've given in this slide all the particulars that will be required for design. So load combinations, moving loads, wind actions, temperature actions, steel structure design, plated structural elements for LTB, the lateral torsional buckling, and so on. So this list is by no means exhaustive. Any of the codal provisions may also refer to additional codes, and the user must be careful in this regard. Furthermore, there are some provisions that are not actually available in the Eurocodes. These will be available in the national annexes, or if they're not in the national annexes, they will be in the non-contradictory documentation, published documents, and design guides. Particularly, I would refer our attendees to design guides by Thomas Telford. So let's start off with the very basics of limit state design. We have two basic limit states, ultimate limit state and serviceability limit state. For steel girder bridges, the ultimate limit states demand bearing resistance, shear resistance checks, lateral torsion buckling or LTB checks, and fatigue resistance checks, while the serviceability limit states deal with deformation, crack control, and stress checks. Now, to start out with, the basic procedure of the design check would be to first of all classify the steel section. So this classification is done as per EC3 1-1. From this slide, you can quite easily see what each class deals with and what kind of section each class is. Now, plate girders in bridges are often in class 3 or 4. Composite sections in sag moment regions are often class 2. In hogging regions, they can be either class 2, 3, or 4. The main reason, although class 1 can be used, but it rarely offers any real advantage over a class 2 section for a bridge. Also, a point to be noted is that for elements that do not meet class 3 criteria as per EC3 1-1, class 4 effective area has to be calculated as per EC3-1-5 and EC3-1-4. So the EC3 code actually makes references to 3 different codes for section classification. Coming on to the bending resistance of sections. So plastic bending resistance for classes 1 and 2 has to be taken for classes 3 and 4, which are not able to assimilate plastic bending resistance. Their checks have to be done using the elastic bending resistance. So plastic bending resistance, or MPLRD as it is denoted in the Eurocodes, is for the effective cross section. So allowance for shear lag and local buckling has to be made for class 4 sections also. So the elastic resistance for classes 3 and 4 can be calculated from this equation. Now, this equation is not directly given in the Eurocodes. This has been taken up from the design guides, and SCI, the Steel Concrete Info Institute's printed document on composite bridges. So this particular equation is normally used for calculating the elastic moment of resistance, and here you can see MAED is the design moment in composite section, that is design moment in the steel section, MCED in the composite section, while K is an amplifying factor that causes the stress limit to be reached in steel or reinforcement, whichever is first. Okay, shear resistance in beam webs. Now, in composite beam sections, shear resistance is simply taken as that of the steel section. There are two basic components, that is vertical shear resistance and buckling shear resistance, and both are dealt with separately, but both are taken from EC3. For shear buckling, contributions from web and flange are dealt with separately, and for the contribution from the flange, in case of composite beams, the bottom flange should be used for shear resistance even if it is larger. Now, this is contradictory to what EC3 would normally suggest. In EC3, you would find that the contribution of flange should be taken from the smaller flange. However, in case of composite sections, because the smaller flange is actually because the top flange is actually connected to the concrete section and therefore offers a lot more rigidity, the bottom flange is considered almost always, even if it is larger. A point worth noting here is that EC3 adopts the rotated stress field model, which is just a modified version of the tension field model, which is used in PS 5950. Both, however, give quite similar results. Coming on to a little bit about the bending and shear interaction. So this graph has been taken from EC4-2 for bridge design. So the bending and shear interactions, and you can see the cutoff for classes 3 and 4. So a few points to note here are that full resistance for shear can only be mobilized in the absence of bending. As bending increases, shear resistance contribution of the flange gradually reduces to 0. And only the shear contribution from the web, that is the buckling resistance of the web, is taken into account in case of the full mobilization of the moment resistance. In case of axial stresses, bending resistance is reduced by a reduction factor, which will be available in EC3 but follows the same general curve. Full plastic bending resistance of the sections can be sustained at the same time as shear resistance of half of the resistance of the web alone, except in classes 3 and 4. Furthermore, EC3 recognizes that close to a bearing stiffener at a support, the shear buckling effects are small, and within a small height, which is within the height of web by 2 of the support, it allows for the interaction to be calculated based on plastic shear resistance instead of buckling shear resistance. So what that means is, in the vicinity of a bearing stiffener, the plastic shear resistance can be used instead of the buckling shear resistance. So speaking of buckling resistance, normally composite beams do not buckle in the classical sense. There is no real lateral torsional buckling, but rather there is actually a distorsional buckling. This is because the top flange is rigidly held in place by the slab, but the bottom flange is relatively free to move. So for composite beams, buckling usually happens in the bottom flanges, especially when they are in compression. Here the buckling is not really the true LTB, but rather distortional, and nevertheless we perform checks for both the LTB check as well as the total distortion check. So EC3 and 4 have prescriptions based on these. These sets of equations are used to calculate lateral torsional buckling. So, but the buckling resistance is chi times the moment of resistance, and a non-dimensional slenderness ratio is used in this case. So I have not taken I have not given the relationship between chi and lambda. These can be seen by the viewers from EC3-1-1. Now, MRK is the characteristic value of bending resistance, while MCR is the critical elastic moment. For hogging regions of composite bridges, it is actually sometimes difficult to find theoretical models that have realistic values of MCR. So EC4 refers actually to EC3-2, which has two different methods for non-dimensional slenderness ratio calculation, the general and the simplified method. So MIDAS Civil goes with the general method. Furthermore, a simplified method for calculating LTB as outlined in Eurocode 3-1 is actually when you approximate the grillage frame in the form of compression cord models. So this is given in EC3-1-1 as the equivalent strut model. So what this does is it considers a model of a compression cord of a truss or a compression flange of a beam, and it considers as if it is held in position laterally, which the lateral supports are depicted by the springs, and the lateral buckling of the compression flange is considered when it is restrained at intervals. Now, this method is primarily intended for a U-frame type bridge. However, it can be used in the hogging zones of steel and concrete composite constructions as well. And another point to note is that in this simplified method, torsional moment of inertia of the beam is ignored. So this simplification can become quite over-conservative for shallow rolled steel sections, but for built-up sections of fabricated bridge girders, it is quite okay. The spring stiffnesses are calculated from this value called CD, which you see the equation over here. So the definitions of the key parameters of CD are seen from this image to the right of it. It should also be noted that this formula makes no allowance for flexibility of joints, and joint flexibility can significantly reduce the effectiveness of the U-frames. So now the Eurocode does not specify the reduction factors for joints to be considered during LTB. For the UK annex, in fact, even the UK National Annex does not specify it. This is referred to in a published document coded 6695-2. So this particular value can be referred to from the published documents and should be referred to in case of joints. Some other effects in main girders you can see here, particularly in the main composite girders, include restraint effects in integral bridges. So the restraint effect again is not specifically defined in EC4. This equation I have taken from the interaction equation in the designer's guide to EC3, which the authors refer to as usable even for composite construction. Now, beams curved in plan or flange curved in elevation. So any curvature of any sort in any dimension induces radial forces. So radial forces then necessitate the provision of lateral restraints at various intervals. Also, plan bending from interaction with cross girders is of special concern in ladder deck bridges, where vehicle loading may actually induce lateral actions. So eccentric vehicle loading particularly can induce significant lateral forces in ladder deck bridges, which have to be taken into account. Finally, the last topic of ULS is fatigue analysis. So fatigue is dealt with very, very extensively, but also very, very non-specifically. Eurocode actually describes two basic methods for dealing with fatigue. These are damage tolerance and safe life. So this is a basic overview of both of these methods. So damage tolerance can be thought of as a very larger. Sorry, the damage tolerance method is not normally used for the bridge types. In bridges, we almost exclusively go for safe life method. For more details about these methods, one can and should refer to the national annexes. Now, in safe life method, the verification is done based on either a damage equivalence factor or on a damage accumulation method. So this you may be familiar with is called minor summation. For highway bridges, damage equivalence factor is almost exclusively used. So damage equivalence factors are typically found for 2 million cycles of loading. Now, EC4 specifies the use of load model 3 for simplified fatigue calculations. Now, the basic steps for fatigue analysis are: determine the stress range delta sigma p due to the passage of the load model 3, determine the damage equivalence factor lambda, which can be seen from the equation below, determine the design value of stress ranges, which can be seen from the last equation at the very bottom of the slide. So you can see delta sigma E2 is the average or mean stress range, the mean factored stress range for fatigue calculations. And the final basic check for fatigue is this particular equation. The factored mean stress range should be less than the reference fatigue value, again a factored value. So delta sigma c is the reference value of fatigue strength at 2 million cycles, which is numerically the same as the relevant detail category according to the EN 1993-1-9. So this particular code, EC319, is the code specifically dealing with fatigue and should be referred to extensively for fatigue analysis. Coming on to serviceability. So there are three basic categories of actions, three basic categories of the combinations that are proposed by the Eurocode. The characteristic actions, which are normally used for irreversible limit state, for example, exceeding of some cracking limits in concrete. Frequent actions, which are normally for reversible limit states. Quasi-permanent, which is normally used for assessment of long-term effects. For example, accounting for creep in the deflections and in the crack control. Stress checks. So stress checks are done as per SLS combinations, and the basic requirement of SLS stress checks is that the structure should be elastic. Stress limits in concrete, steel, reinforcement, and studs are reduced by certain values, which are known as K factors for the SLS stress checks. So K1 is for concrete, K2 is the limit for concrete in quasi-permanent combinations, K3 is for reinforcement of slab, and Ks is for shear studs. So EC4 refers us to EC32 for the deflection limits, and basically deformations are calculated from the frequent load combinations. Also, EC3 is silent on any actual deflection limits. So familiar limits like L by 250, L by 300, these are not actually defined in EC3 or for that matter EC4. So normal practices normal reference practices, normal values based on experience, as well as the national annexes should be referred to. Finally, regarding crack control. So Eurocode is fairly straightforward when it comes to crack control. The Eurocode advises EC4, which prescribes minimum reinforcement in lieu of a more accurate method, which most people would rather not use, and describes this as a conservative approach, so it is quite fine. So this is the minimum area of steel that should be prescribed as per the Eurocode provisions. So certain factors are used over here. I will not go into the detail of what this equation entails or what these factors are. They can be referred to from the pertinent Eurocode. Furthermore, the Eurocode also imposes a maximum limit on the reinforcement amount. So the maximum bar diameter and the maximum bar spacing is also prescribed based on the amount of stress in steel. Linear interpolation between these values is, of course, allowed. So that was a little bit of discussion about the Eurocode provisions. Let me now go ahead and show you how MIDAS deals with Eurocode design. So first we'll quickly create some load combinations. Now, depending on the load cases that we have created, the load combinations will be also created based accordingly. So I have to create it in PostCS. So I will get some load combinations like so for concrete design. Similarly, I will get load combinations for steel design as well. So I'll need just these two separately, the concrete design as well as the steel design. Coming over to the design tab, I will go ahead and describe to you how MIDAS, how you can use the MIDAS composite section design options. So composite section design can be dealt with. So under this parameters, if your national annex is not supported, you can easily change the parameters from here. For example, I will change it to the normal concrete parameters, for example, 1.5 and 1.15. And for gamma M1, it is 1.1 as per the British code. So all the factors can be changed based on the national annex recommendations of your particular region. The design material. So the material should be an SRC material, and here you can choose the design material. You can also choose user-defined material types if you do not want to go with a particular predefined material. So just define the reinforcement grade, and now we define some longitudinal reinforcements. So for longitudinal reinforcement, we can very quickly and very easily define it. So let's say I want 15 bars of diameter 10, or let's say in case diameter 14. So I begin to enter it like this. I'm just clicking and dragging my mouse, and I define it as an edge bar. So like this, and I click on add. Similarly like this, and I click on add. So in this way I can define my reinforcement. I've already assigned it same rebar data at I and j end. I can also define shear reinforcement from this tab itself. For simplicity, I'm going to leave it as is. Furthermore, I can choose a design position. So for this particular model, I'll simply choose all the main beams. Normally you would choose like the design position to be the position for critical forces and critical stresses, like at the support ends and at the midspan sections. So you can do that also. You can define longitudinal stiffeners if you would want to have any longitudinal stiffeners in your model. Furthermore, shear connectors. Now I will define some shear connectors. So let's say I have two connectors per two shear studs across the cross section of my steel section, and a high tensile strength, 25 millimeter diameter, overall height of 100 mm, center to center distance, let's say I call it 75 mm, and 150 mm longitudinal spacing. So in this way I can even define the shear connectors. Although they are not displayed, but they can be looked at from the design table. So you can check how the shear connectors have been entered by referring to design tables, shear connector. Similarly, you have options for transfer stiffener or transfer stiffeners at end support for taking into account the shear resistance, the plastic shear resistance at the end support at the bearing stiffener level. Similarly, for LTB, the lateral torsional buckling, which I had described to you using the equivalent strut model, you can define the distance between the springs. For example, in this case, let's say I have let's say a stiffener is being provided at every 3 meters. I'm assigning a random spring stiffness and an alpha value should be greater than 1. The spacing between parallel beams, of course, is also 3 meters. Now, the damage equivalence factors and other things. So these damage equivalence factors you can look up from the Eurocodes. So this is obviously for the fatigue analysis. So when you conduct design, MIDAS will take some time. It will conduct the overall composite steel design, and at the end of it, it will give you the design results. So the design result tables include the bending resistance, so you can get the overall bending resistance. Furthermore, if any sections are failing, so here you have the, if any sections are failing, it will show that element in red. So the fact that it is showing everything in black means the section is passing. Design resistance, resistance to lateral torsional buckling. So this is buckling, and here you can see the interaction ratio. So the interaction ratio based on the equation, the linear equation N upon NRD plus MED upon MRD should be less than or equal to 1. So all of these are less than 1. Resistance to longitudinal shear and everything. Resistance to fatigue. So even fatigue calculations have been taken into account. Since we have not defined the particulars for the serviceability, so the serviceability load combination types have not been defined, so they have not been included in the analysis. So you can manually define it and you can manually include it as well. And perhaps the best part of all is you can print an Excel report. I'll repeat this, you can print an Excel report for your design results. So since this will take a bit of time, I have a pre-made report in Excel that I will show you. So this is just done for one element at one position, but you can very clearly see it is presented in a very orderly fashion, and perhaps the best thing of all, it uses the actual equations. So the actual equations are being used, which you can verify from the Eurocodes, and it tells you exactly what the value is, how the calculation has been done. So it becomes very easy to manually cross-check the calculations. So finally, if you would like to include the program results in a report, for example, let's say I would like to include the bending diagram, or if I would like to include any particular table in a report, how can I do that? So the option here is just right click, go to dynamic report image. Even in a table, just right click, dynamic report table. So when I close this, I get under the report tab, I get these options. So beam diag and my tables are already there. And finally, I can just go to dynamic report generator, open up a new document, and I can create my report quite simply by just dragging and dropping my images. So I just drag and drop my image from the works tree into the Word file, and this is actually a Word file. So all your templates, your Office templates, everything, so your normal workflow will be preserved, and you can pretty much work on it as you would normally a Word file. So your user-defined tables can also be dragged and dropped. So this kind of a table will be available to you. So you can directly work on your report within MIDAS Civil itself, dragging and dropping and creating your report with a lot of ease. Okay, so coming on to the final leg of our presentation, and that is BS code versus EC. What are the differences between the two? So at first glance, it would appear that the Bureau code is very different, but actually the two are more closer than they look. The differences are not that many, and in fact, the design practices are quite similar in both, just a difference of a few constants. So the first major difference between the British code and the Euro code is the concrete strength. So British code takes the concrete strength from the cube, while the Euro code takes concrete strength from the cylinder. However, when you convert the concrete strength to the equivalent plastic stress block, so the factors are actually 0.67 for the BS code and 0.885 for the Euro code. So the two factors actually end up giving almost practically the same result, as you can see from this small example that I have given over here for calculating the concrete strength for British code and for Euro code. So as you can see, there's not much difference at all. Coming on to the difference in shear connectors. Now this is a slightly significant difference. In BS code, the characteristic strength of studs is given for various combinations of height, diameter, and concrete strength. But Euro code takes a more theoretical and systematic approach. It calculates the resistance as the minimum of two equations. The first one is for the failure of the stud in shear. The second equation is for the failure of concrete by crushing. The following graph shows a comparison for stud resistance between EC4 and BS 5950-3. Now, it should be pointed out that this graph assumes that the failure of concrete by crushing is the dominating failure mode in the majority of stud failures, and this is usually true because for the nominal shear studs, the shear resistance of the stud generally exceeds the crushing strength of the concrete. However, for higher grade concretes, the inverse is true, which you can see in this graph that beyond FCK 30, it can be assumed that the strengths begin to match. Another point of difference between the two codes is that BS code simply states the minimum shear connection requirements as a function of span length, but Euro code considers the asymmetry of the section also. So particularly EC4 has to be referred to for the asymmetry parameter variations. Effective width calculations. Now, as per the British code, the effective width equals span by 8, and it is subject to some basic conditions like the transverse span length. However, for Euro codes, it varies along the length of the beam, and from this image you can see the basic variation of the effective length. Now, for most beams, however, the critical section is actually at the center, where the effective width is the same as the BS code. The variation of effective width might seem important for serviceability cases, but in case of serviceability, the Euro code allows the same effective width as the midspan to be used throughout. So what do I mean by this basic explanation is that the effective width calculation is practically the same for both BS code and for the Euro code. I'll repeat it, the effective width calculation is practically the same for BS and Euro codes, and you can keep on using the British code effective width parameters if you have been using them. The final point of difference is the different shear areas for the British code and the Euro code. So the shear area is actually slightly larger for the Euro code than it is for the British code, and therefore gives a slightly higher shear resistance for the Euro code. For normal U-frame sections, it can come out to about 6% higher for the Euro code than for the British codes. So with that, I would like to bring this presentation and this web session to a close. Once again, I would like to thank you all for your time and for the time taken, for giving us your precious and valuable time. If you have any questions at this moment, I would be more than happy to address them.